So I don't know if you watched the video, probably you haven't, but it's okay. I introduced this idea of capacitance and capacitors. So capacitance is the ability of an object to store charge. Plays a lot of different roles. It's more complicated than that, but the simple way that we look at it at first is capacitance. So I'll give you the 5-minute version of what I did on Monday. Capacitance, which we'll use C, that is not coulombs, all right? Capacitance is charge per unit voltage. So it's coulombs over volts. Or coulombs per volt. That is called a farad, named after Michael Faraday, and it's capital F. So when you see me write capital F, that's a farad. Capacitors, we looked at a simple, probably the simplest case, which is a parallel plate capacitor. It's just two plates separated by some distance d, and you get an electric field between the plates. You're storing charge on the plates. You get an electric field between the plates, and there's energy stored in that electric field. So for a parallel plate, the capacitance is equal to epsilon naught times the area of the plates over the separation distance between the plates. So you can think of, two square metal plates separated by some little distance. All right, this is the way you would calculate the capacitance. So the capacitance, even though it's charge per unit voltage, when you end up calculating the capacitance of a capacitor, so a capacitor is the little component, you get something that depends on just the geometry of the capacitor, the materials maybe that it's made with. Okay, it's independent of charge and voltage. We looked at some combinations of capacitors. So caps in parallel. Caps in parallel. Parallel refers to how they're connected. Caps in parallel, they look or they're connected just like resistors in parallel. Here's C1, here's C2. To find the equivalent capacitance for caps in parallel, you just add them up. So it's the opposite of resistors. For resistors in parallel, you have to do the 1 over thing. So C equivalent is C1 plus C2 plus ... as many as you have in parallel. So the equivalent capacitance in parallel is always larger than the largest capacitor. They all have equal voltage, and the largest cap has the most charge on it. Because I can move this equation around, just like we did with Ohm's law in the lab, and C times V is equal to Q, and interchanging those, you get V is equal to Q over C. All right, so if they all have equal voltage, the largest cap gets the largest charge. Okay. Caps in series. The wiring is just like resistors in series. C1, C2, as many as you want to put in series. And the equivalent capacitance in series works like resistors in parallel. So the equivalent capacitance here, you calculate this way. 1 over C equivalent is 1 over C1 plus 1 over C2 plus ... as many as you have in series. I usually do them 2 at a time. If I have 10 in series, I don't know. Yeah, probably do 2, 2, 2, 2, okay? And C equivalent is equal to C1, C2 over C1 plus C2. Caps in series have equal charge, always. So no matter the size of the caps, if they're in series, they're both going to have the same amount of charge. So the smaller cap has the largest voltage, okay? The larger cap has the smaller voltage. The series equivalent capacitance is always going to be less than the smallest cap. Okay? All right. That's everything I did on Monday, except we started analyzing some circuits. So we're going to do that now. So I mentioned, this is like a recipe. You learn the recipe and you apply the recipe and everything's beautiful. So we're going to draw a circuit, or I'm going to draw a circuit, and we'll reduce it down to an equivalent capacitance for the circuit. Then we'll work backwards and figure out all the charge and all the voltage on each one of the caps. Okay? So there's the battery. There's the first one. I'll make it a little more complicated than I did on Monday. That's enough. So here's 15 volts. I'll make this a 2 microfarad, 3 microfarad, 5 microfarad, 7 microfarad, and let's have another, let's see, that's 3, 6, let's have a 4 over here. That way they're all different. We can tell which one we're talking about. Okay. So here's a network of capacitors. The first thing to do is reduce it down to 1 equivalent capacitance. And where do I start? What do you see that's maybe in series or parallel that I can combine and get an equivalent capacitance? The 5 and the 3, right? I mean the 5 and the 7, right? They're in series, okay? So I redraw the picture every time. I would recommend that you do that as well. Maybe you're faster and better, and you don't need to, but I do. Okay. 15 volts, this is a 2. This is a 3. This is a 4. And now this one hanging out here, since we have a 5 and a 7, that's 35 over 12. Microfarad. 35 over 12. Okay. I just came from C1 times C2 over C1 plus C2, if you're wondering where I got that. What's next? Yeah, the 3 and the 35 over 12 are in parallel, so we just add them up. So here's the... Okay, this is still a 2. This is still a 4. And now this becomes 71 over 12. We'll get to the decimal equivalents in a minute because we're going to need them, I think. All right. What now? Well, you can do 1 over this plus 1 over this plus 1 over this is equal to 1 over C equivalent. Maybe that's the best way to do it because those three are in series, right? You have 3 in series now. Can somebody calculate this? I would do, if I'm doing it on paper and I'm working by hand, I would put these in series, then I would put that equivalent in series with this and get the number. Can somebody tell me what this is? And you can just give me the decimal equivalent. That's a 2. That's 140. That's 142 over 12. Oh no. Yeah, 142 over 12 divided by 24. It's 29. No. It's 95. So this becomes, I think this becomes 142 over 95. And then in, all right, that's 566 over 95. 95. And then, yeah, ooh, I don't know. What do you get? What do you get for those 3 in series?
11.9167.
What size?
11.9167.
It's got to be less than 2. Let's do it. I mean, you got 1 over C equivalent is equal to 1 over 2 plus 12 over 71 plus 1 over 4. And good luck finding a common denominator there.
I got 1.09.
1.09? Okay. 1.09 microfarad. Yeah, that's more reasonable. Can anybody confirm or deny that calculation?
I vote 0.9.
You got what? You got 1.09?
Yeah.
Okay.
I was thinking about circuits with resistors, which is like the opposite.
Yeah. Yeah. Okay. All right, I'm going with 1.09. Okay. So the equivalent capacitance for this entire network is 1.09 microfarad. I know the voltage, I know the capacitance, I can find the charge because voltage times capacitance equals charge. So the charge here is 15 point something microcoulombs. What, can somebody calculate that? 1.09. Try to keep all the digits for those of you that are calculating for me. Might be 16, but I don't think so. What do you get? 1.09 times 15. Just tell me what that is.
16.3.
Okay, 16.3. Everybody agree with that? 1.09 times 15.
It's 16.35. I don't know if you want to run that.
I thought looking at it was 15 point something because that's 1. And what'd you get? 15?
No, 16.35.
Ah! Okay. 16.35. Yeah. Okay, we'll go with that. I made it too complicated. All right, here's the point. We've got the equivalent capacitance for the entire network. We know the charge on the equivalent capacitance. This came from a series connection. Caps in series have equal charge. So whatever charge is on that equivalent capacitance, that's the same amount of charge on each one of these. So this one has 16.35 microcoulombs. This has 16.35 microcoulombs. And this has 16.35 microcoulombs. Okay? Now that we know the charge on each one of those, we can calculate the voltage on each one of those caps. All right? Because voltage is equal to charge over capacitance. So this one is 175 volts. 16.35 divided by 2. This one is 16.35 divided by 71 over 12. That's about 2 point something, I guess. What do you get here? Charge divided by capacitance. 16.35 divided by 71 over 12.
2.76.
Okay, 2.76 volts. Then this one's 16.35 divided by 4, which is about 4 point something.
0.875.
What?
0.875.
4.0.
0.875.
Agreed? Okay, so these should add up to 15 volts. 8, 10, 11, yeah, okay. All right. We're done with the 2 and the 4 because we know the charge and the voltage, the charge and the voltage on each one of those. Okay. This capacitor came from a parallel connection. A parallel connection here. So we're guaranteed that each one of these will have 2.76 volts. Caps in parallel have equal voltage. Oh, by the way, over here on this series connection, the largest cap, the smallest cap got the largest voltage. That's expected. Because they all have equal charge, so the smaller cap or the smallest cap needs more voltage to have that amount of charge on it. Okay, we know the voltage, the capacitance, we can easily calculate the charge, because that's just capacitance times voltage. So this becomes, what is this, 3 times 2.76. What do you get for that? 8 point something. Can somebody calculate that, please? 3 times 2.76.
8.2.
8.28. 8 volts. I mean, microcoulombs. And this one, 8.07. Is that right? Who's calculating?
Yeah, it's 8.05.
8.05, okay. I know we got rounding stuff going on. Okay. We're done with the 3. We know the voltage, the charge, fine. Now, this came from a series connection. The 35 over 12. So each one of these has because they have equal charge, microcoulombs, 8.05 microcoulombs. Now we can figure out the voltage on each one of those, because voltage is Q over C. Q over C. What do you get here? 1 point. Total voltage, okay. What's the voltage on the 5?
1.61.
1.61. And here, 1.15. What do you get here? 1.15. Okay. Finished. For each one of the capacitors, we know the charge and the voltage. That's the recipe. Work down, find the equivalent capacitance, go backwards using these rules of series and parallel. Series, they have equal charge. Parallel, they have equal voltage. Okay. Thank you for your help on the calculations. Any questions on this? Okay. Capacitors store energy. I already mentioned that. The battery or power supply has to do work to place charge on the plates of the capacitor, and it does that work against the electric field. The energy is stored in the electric field. If you're looking at let's say you have a parallel plate, simple capacitor, you're looking along the plates. There's plus charge over here. Let us say there's negative charge on this side, and that produces an electric field between the plates in this direction. So there's some electric field based on the amount of charge and the capacitance. Okay. So there's some electric field in there, E. We're going to find out in lab, if you haven't already done lab this week, that we can reap this energy. We can hook it up to a circuit, and this electric field will push charge around the circuit and do work. So the energy stored in a capacitor, I'm not going to derive this. U is equal to 1/2 CV squared. Okay, it's that simple. It's like kinetic energy. It has the same sort of form, only that's not velocity and that's not mass. So it's 1/2 CV squared. You can make a substitution because V is Q over C. So you get 1/2 Q squared over C. All right. That's the energy stored in a capacitor. So let's say you charge up a capacitor, just to give us an idea of, say there's a simple circuit, 5 microfarad, and this is 15 volts. Let's go ahead and calculate the charge that would be on this. So if you have 15 volts and 5 microfarads, the charge is CV. So this is 225 microcoulombs, right? 75. I'm thinking 15 times 15. Okay. 75. Thank you. Okay. How much energy is stored in the capacitor? Well, you can use either one of these. The thing you have to be careful about is make sure that you put the capacitance in farads. If you're using this one, make sure you put the charge in coulombs. So U is equal to 1/2 5 times 10 to the negative 6 farads and 15 volts squared. So this is equal to what? That's not, that's a 2. Supposed to have been a 2. Anyway, can somebody calculate this, please? $11.25, 5 point something.
5.63 to the negative 4.
5.63 times 10 to the negative 4 joules. Okay. So in a circuit, in a more complicated circuit, like the one we just did, I could ask you how much energy is stored on each cap and so forth, okay? You can also use, you can check me, but you can use Q squared over C. That should give you the same answer. Okay. So 563 microjoules. It's a small cap, pretty low voltage. Right. I think that's all I'm going to say about caps energy stored in caps. Is this thing still spinning? Oh, okay. I want to talk about dielectrics. Most capacitors that you would purchase will have some sort of dielectric in them. So dielectric is just a material that increases the capacitance of the capacitor by being in between the plates. So when we were talking about electric fields and charge and so forth, I didn't really have time to talk about dipoles. But you can think of it like this, plus, minus, here's an atom or a molecule, and because of the structure of the atom or the molecule, there's some separation of charge. All right, the charge is bound in the molecule, but there's a little bit of separation between it. All right, so you get an electric field due to the dipole that's in this direction. Okay, it goes from plus minus. You get a little tiny electric field vector in there due to that separation of charge. Water has a dipole moment. Water is a dipole. What's the structure of water? H2O. It looks like Mickey Mouse, right? It doesn't really look like this, but okay. Here's H, and here's H. Okay, there's a big O and two little ears that are the hydrogen molecules, or atoms. What's the angle here? (105 degrees), something like that. Anyway, ask the chemist, okay? Anyway, water has a little dipole moment, meaning there's a little separation of charge due to this structure, okay? Anybody know how a microwave works? It's just magic. You don't care, it just heats your food, right? Okay. It does rely on water, yeah, for the most part. Yeah, because what's going to happen, let me ask you this, if you have a little dipole, I'm claiming water has this so-called, I haven't even defined it, but it's called a dipole moment. It means there's a little separation of charge and there's a little electric field there. What's going to happen to that little separation of charge if you place it in an external field? Let's say there's a field this way. No, let's go this way, the other way. There's an external electric field, not this internal field, but I placed that dipole in a big external field. Well, think about what is the charge? How's the charge going to react to this that's in the molecule?
Don't they separate from each other?
Yeah, they do separate a little. Well, I'm thinking of a uniform electric field, so it's uniform over this little small distance. You're right, though. If it's a non-uniform field, they will try to separate somewhat. Isn't this thing going to try to line up with the field? Because the positive charge is going to be pushed that way, and the negative charge is going to go that way. Yeah? Okay. So in a microwave, because water has this ability, okay, to rotate in an external electric field, what happens in a microwave is you have a microwave gun. Remember the electron gun in the CRT? You have a microwave gun, so it's emitting microwaves. That's an electromagnetic wave. It's a long wavelength wave. Electromagnetic waves have an electric field and a magnetic field. So this microwave gun that's in your microwave starts emitting these electromagnetic waves, so they have an electric field. And then there is this thing that you hear come on, and it sounds like a fan. There is a fan that comes on, but there's another thing that comes on called the stirrer. These microwaves from the gun are fairly regular, and then they interfere with this thing that's going round and round, and it starts mixing up the microwaves. Here's the cavity of the microwave oven. It starts mixing up the microwaves, and they get all randomized, and they start bouncing around in the cavity of the microwave. this dipole moment that's in water starts to react to that changing electric field. So these water molecules start to rotate, and it's friction. They start to rotate, they rub each other, and they get hot, they heat up. That's why if you put ceramic in there, the ceramic doesn't get hot. You put a coffee cup in there with nothing in it, if it's a nice ceramic cup, it doesn't get hot. You don't have any dipole moments. You don't have any of these little dipoles to rotate and get warm. But things that have a lot of water in them and other chemicals as well, you put them in this changing electric field and they'll start to rotate, bounce around, they get thermal agitation, and they heat up, okay? You know that little thing you look, the little window you look in on the microwave, it's got all those little circles? It's got all those little holes? Anybody know why it has they always have that little mesh? Go ahead.
Is it having something to do with like the shell, like you're protecting the electric?
Yeah, that's like a mirror for microwaves. A mirror for visible light is a silvered plate or silvered glass. But for microwaves, this structure of these little circles and so forth, it's like a mirror for microwaves. They're long waves and they interfere with this structure and they bounce off. Okay? So you got to have the microwave gun, you got to have the stirrer, and if you want to see in it, you got to have the little honeycomb thing. Not really, what is it? Little circles.
Is that why we don't put like foil into a microwave?
Yep, because what happens with foil is you start moving it's a conductor. You start moving the electrons around, you're creating a current, and you get high currents, and pow, it melts, it starts crackling and all that stuff. You can put metal in a microwave depending on the structure, and it won't do much harm. But yeah, those electromagnetic waves are creating currents in the conductor. What they're doing in the water is just making the water molecules move around and agitate and get hot. Okay. So, back to the dielectrics for the capacitors. Dielectric materials have these little dipoles in them. Typically in a dielectric material, like you would have in a capacitor, those little dipoles don't move around like you would in water, like a liquid where the dipole can sort of move around and rotate. So they don't translate, but they rotate. So they're in a crystal of some kind and they're able to sit there and rotate, but they can't translate, okay? So let's take this parallel plate capacitor. Again, here's plus, minus, plus, minus. Okay. And we connect it to a power supply or a battery. Okay. And depending on the separation distance of the plates or the capacitance, you get an electric field inside the capacitor. I'll make a different color. There's an electric field inside the capacitor based on the amount of charge that's stored on the plates, okay? I'll call that field E. Yes?
Is it uniform?
What?
Is it uniform?
Yes. Watch the video from Monday. I use Gauss's law to calculate the electric field inside the cap. Okay? It's two parallel charged plates. So like what we did with the calculating the electric field for the disk, and then we let that go to infinity. We said, okay, you get this nice uniform electric field that doesn't vary anywhere and all, yeah. So you got two parallel plates with those uniform fields, and you get a very uniform field inside the capacitor. On the edges, different things are happening. But if we're inside, okay, we're making some assumptions and some simplifications. All right, but yeah, we're saying there's a constant uniform, well, if I say it's uniform, that means constant, but there's a constant field inside. Then you insert a material called a dielectric in your capacitor. And it has those little dipoles in it. What's going to happen? Those dipoles are going to line up such that the positive charge, I know maybe you can't see this, but the positive charge is over here on the right, and the negative charge is on the left. Those little dipoles start lining up. They have an electric field in this direction. I'll call it E. I'm not going to do the calculation, but that's E sub D. That's the electric field of the dipole. So the net electric field inside the capacitor goes down because you have the electric field due to the charge stored on the capacitor, and then this electric field from all these little dipoles lining up. So what happens is V is equal to E, not E sub D, but E times D, where this is the separation distance of the plates, since I'm talking about a parallel plate cap. So you're able to store a lot more charge on the capacitor because the net electric field is less for a given amount of charge because you've got that dielectric material in there. And we can talk about energy, what happens with energy, how the energy changes and so forth. But that's what happens. So you increase the capacitance of your capacitor. C is equal to kappa C naught. So this is the original capacitance, and this is called the dielectric constant. Kappa. It's that funny looking K, Greek K. Kappa is greater than 0. It increases the capacitance of the capacitor. All right. It may be, it may be 2, it may be 3, it may be 5.7, depending on the material. Paper is a good dielectric material. Plastics, what do we got? 3 minutes. Okay.